fourth video for section 2.2 lecture. Let's go back and just analyze this a little bit more. We have that this information, we've defined what it is. Sales have been increased this much per year for each additional year in 2001, and in 2004 sales increased by this much per year. Let's take a look at this graphically though and see what happens. So now that we've defined the function, let's go in and pick up a graph page and let's take a look at the function. And it doesn't look like a lot, but we're going to change the window so we can see the actual function. Okay, so let's look at a window, and a window setting that will fairly show everything that we need to know. Let's make this -1 and 20, and let's scale it by let's just say every 5, and then -100 up to 2500, and we'll scale it by 500. So if we have that kind of a window, we'll see for the most part what we need to see on this. There we are. There's our function, and the yeah, can't even get all the function in there, but anyways, the function. Okay, you know the routine then. Let's put some points on, and we're going to actually put 2 points on the curve. So put 2 points anywhere on that curve. Let's change the coordinates. We want one to be at 11 input, and the other one we want to be at 14. Now, although it's not important to know what the output values are, let's see if we can come up with this. E plus 3 means that it's in scientific notation. Take your cursor and just hover over that, and then if you come over here and press the subtract key, you're going to get a value. If you use the plus key, you're going to be increasing the digits, and so you can just hover and get it into something that looks a little more familiar. We can do the same thing with that one. Just sit there and hover and then press the negative key or the positive key, and you will increase or decrease the number of digits on that. Again, we don't need to know those values. We're interested more in the tangents that we have, so I'm going to move these coordinates around just a little bit here. So let's go into our menu, and let's draw tangents at these junctures. There we go. Now, if you notice, isn't it curious? Look at this tangent. This tangent at 11 actually crosses the if I can get that to pick it up. Anyway, actually crosses the graph right there. That's why we had to change our definition of what tangency is. Now, we're interested in, over here, our derivatives are interested in the derivative, in other words, the slope of those tangents. So let's go into Menu, Measurement, and Slope, and let's look at the slope of that. It's actually not 0. It looked like it was pretty horizontal, but it's not. And the slope of that. How do those correspond? Well, they're not as many digits, obviously, so I'm going to do my same thing I did before. I'm going to hover there. Let's see if I can get my cursor to hover at that point. And then add the plus key, and that's going to increase it. I can do the same thing here, hover, and I can increase, although it looks like it's a pretty solid value, although I don't believe that to be true. But if we hover there, and then we can increase by using the plus key. There we go, the plus key. So we have then that those values do work. So the sales, the increase on sales is increasing more dramatically. We're getting more sales per year. Sales is increasing more per year at 2004 2004 than they were at 2001. 2009 would of course be back here then on the curve, and we would have then another increase. So it's kind of leveled off at this point. And if you were going to advise the group, you would say, well, it's leveling off, but it's going to be going back up, and we're going to be increasing then again. Each year, the increases are going to get larger and larger. Okay, one last problem for this section, and we've already answered that question. Okay, here we go. For this function over the interval from 0 to 3, recall this means that 0 is less than or equal to x. Because of the bracket, we include the endpoint, less than or equal to 3. That's what this interval notation means. Graph the function and the derivative over the given interval. Well, let's look first at what is the derivative. And again, we're practicing that for this section. So let's see, we've got the coefficient times the exponent, and subtract 1 from the coefficient, or from the exponents, that'd be squared, minus 12 times 2, subtract 1 from the exponent, would be 2 minus 1, or 1, plus 2.5 times 1, because the exponent is 1, subtract 1 from the exponent, that'd be x to the 1 minus 1, or x to the 0, or simply 1. So our derivative then is going to be 12.3x squared minus 24x plus 2.5. So we're going to graph this and look at it on the interval from 0 to 3. Okay, so let's go to the inspires. I'm going to ask you to insert a new problem. So on the click pad, do Control Home, and we have this insert and new problem. If you're on the touchpad, if we just go to document and then insert, we can insert a new problem. So we'll insert a calculator page, or excuse me, a graphing page on this. Let me do that one more time because I did not get a new problem out of that. There we go. And we'll do a graph. Okay, so we're going to insert here the function for 0.1 x cubed minus 12x squared plus 2.5x. And we need to change a window on this, so let's do a window setting of -1 to 4, scale 1, and -15 to 3, scale 1. And we have the function that looks like that. Okay. We also want to graph the derivative, and so we'll take a look at the derivative, and let's graph the derivative. Press tab, and we'll have that back again. So we want 12.3x squared minus 24x plus 2.5. And we have then our derivative. So I'm going to now go into Menu, Actions, and Attributes, and I want to change this to be a little thicker so we can see the derivative a little differently. Now the problem is saying determine the points at which the graph has a horizontal tangent. If we're going to do this analytically, or analytical work would be to determine where is the derivative equal to 0. Any horizontal line has a slope of 0. So we would then have 12.3x squared minus 24x plus 2.5. If you could factor it, you could do that. You could use the quadratic formula. And if you recall, the quadratic formula is x equals the opposite of b plus or minus the square root of b squared minus 4ac, all of it divided by 2a. We can go through and solve that. We would find that x is approximately 1.8408. And by my notes, and we're going to check this, 0.11. So approximately that. Well, let's go over here and see if we can determine. Now, our derivative is the very bold line here. And what we're looking at is, where does the derivative have a value of 0? And it's going to be here. The zeros of the derivative would be here at the input axis. So let's see if we can find something to help us out. If we analyze graph and we look at 0 and we point to this graph, notice down here at the bottom it says lower bound. So let's set a lower bound here and an upper bound here. And then that's the first one. And then let's look at the second one. And let's set the lower bound on this graph. Let's set the lower bound here and the lower bound here. And we get 1.84. Are those consistent with what we have analytically? And the answer is yes. Analytically, do I expect you to be able to use the quadratic formula? Yes, I do. That's something that you can work on. You know how to do. You've had it in many other courses, Algebra 1, Algebra 2, and so forth. But I also expect you to be able to check your work. Now, let's just go through this, remind ourselves how to do this. It would be the opposite of our coefficient here, negative 24, plus or minus the square root of negative 24 squared, minus 4 times a is the coefficient of our leading term, 12.3, times c, which is our constant function, 2.5, all of that divided by 2 times our leading coefficient. Remember, this only works for quadratic formulas, quadratic polynomials. And so if you simplify that, you should have then those answers come up, and we do verify them. Now, let's look and see, on the original function, what do those correspond to? Well, if we were to take a tangent to that point right there, and find a tangent down here equivalent, we would want to know where the tangent line has a slope of 0. Now, I don't know if we're going to be able to pick up that slope or not. We'll just work with this one. And so I would need then to move this around. Now, if I had a point, it would be there. Did you notice what it said, though? It said minimum. And so it's here at the minimum of this. If I draw a tangent line, it would have a minimum, a horizontal tangent line. And so if I pick that up and I find where it says minimum, notice that the slope here, and again I can come over and hover on that and press the negative. Let's see if that's going to work. That's not going to work for that text, but it would be equivalent to a 0 there. So the horizontal tangent lines are where the original graph has what we call a turning point. We're going to be talking a lot about that in the next chapter, but it has a turning point, and those turning points correspond to where the derivative crosses, if we graph the derivative, where it crosses the horizontal tangent line. Okay, that's it for this section, and there's one more section we're going to discuss on this day, and that is section 2.3.